For number 9, we're looking at related rates. The boat is being pulled towards the dock. The person is pulling the rope at a distance of 3 feet from the water to his hand, x. X is 3 feet. If the rope is being pulled at a rate of 3 feet per second, which is dz dt, dz dt is 3 feet per second, and the rate of the rope to the water moving downward, that's why it's negative 2 feet per second, dx over dt, which is negative 2 feet per second. How fast is the distance between the boat and the dock increasing? So then we're looking for dy over dt. That's what we're looking for when the boat is 4 feet from the dock, which is y, 4 feet. So for this example, we're going to need 2 equations. So notice that we have a right triangle, and what we remember about right triangles is x squared in this case plus y squared equals z squared. Pythagorean theorem. Then the second equation is going to be the derivative of that with respect to time. That's the other variable here. So when we take the derivative of x squared, that is 2x dx over dt, the derivative with respect to time, plus the derivative of y, which is y squared, the derivative is 2y, the derivative of y with respect to time, equals then the derivative of z squared, which is 2z, the derivative of z with respect to time. So it starts with these 2 equations. Then we already started filling in what we know. And what we know is x is 3 feet, y is 4 feet, z we do not know, dx over dt is the negative 2 feet per second, dy over dt, that's the one we don't know, and dz over dt is 3 feet per second. Now we're going to use those 2 equations to find those 2 unknowns. So to find the z first, we know that x squared plus y squared equals z squared. So x is 3, so 3 squared plus y is 4. 4 squared equals z squared. 3 squared is 9, 4 squared is 16. 9 plus 16 is 25. Z squared equals 25. So z equals technically positive or negative 5, but the only one that makes sense is the positive 5. So now we found that z is 5 feet. Okay, now we know everything except for dy over dt. So we're going to use the second equation, which is the 2x dx over dt plus 2y dy over dt equals 2z dz over dt. Now we're going to fill in everything we know and solve for what we don't. So we have 2 times x is 3, times dx over dt, which is negative 2, plus 2 times y, which is 4, times dy over dt, which we don't know, 2 times z, which we now know is 5, times dz over dt, which is 3. We're going to work all this out and solve for what we don't know. So 2 times 3 is 6, 6 times negative 2 is negative 12, plus 2 times 4 is 8, dy over dt, equals 2 times 5 is 10, 10 times 3 is 30. Continue the algebra, add 12, we end up with 8 dy over dt equals 42. So if we have 8 times dy over dt equals 42, we divide by 8, we have dy over dt. If you do 42 divided by 8, you will get 5.25, and remember that's a rate, so it's going to be the feet per second. So now we solved for everything. Now, let's work on number 10. So for number 10, it's a similar problem. And again, the end answer is, what is the rate of y? It's 5 feet, 5.25 feet per second. So for number 10, suppose that a company manufactured graphing calculators has a revenue equation of Rx equals 300x minus x squared over 30, where x is the number of graphing calculators. So our input, to be very clear, x is the number of calculators. Our output is revenue. So we'll write that down. Input x is the number of graphing calculators, and our output y is revenue. So if production is increasing at a rate, there's a derivative, of 500 graphing calculators per week, what is that telling us? That is telling us the rate of change. So how the calculator's sales are changing, the revenue is changing, is dx over dt, which is the 500. Okay, that's 500. Again, output over input, the revenue per calculator, revenue over calculator. Okay, then per week, it's over time, so it's per week, revenue week. When the production is 6,000 calculators, 6,000, so X equals 6,000 calculators. Okay, so, and again, we'll get that week in there soon. Find the rate of increase or decrease in the revenue. So if we want to find the rate of change with respect to time. So there's that extra variable, okay? So we'll get that week in there soon. So the revenue, we're going to take the derivative of revenue with respect to time. So the derivative of revenue with respect to time. So we're going to take the derivative of 300x, which is 300, derivative of x with respect to time, minus, this is 1 over 30, so we pull that 1 over 30 in front. Then the derivative of x squared is 2x. Again, that is the derivative of x with respect to time. So when we clean this equation up, we have the derivative of revenue over time with respect to time. We have 300 times dx over dt, which is the derivative of x with respect to time, minus, now we have 2 over 30, which will simplify to 1 over 15 x dx over dt. So we want to find the rate of change, increase or decrease in the revenue. So we're trying to do this over time. So to fill all this in, let's see what we know. So to find the derivative of revenue with respect to time, it's 300 times dx over dt, which is the 500, minus 1 over 15 times x is 6,000, times dx over dt, which is 500. So let's go ahead and put all that in the calculator. I am going to type it in all at once, so be careful typing it in all at once, just to be careful we don't make any little mistakes with the calculator. So in the calculator, we put 300 parenthesis 500 close parenthesis minus parenthesis 1 over 15 close parenthesis times 6,000 parenthesis close parenthesis 500 close parenthesis, and you get negative 50,000. So let's explain this in a sentence. So our answer is negative 50,000. So in a sentence, let's keep it in the same thing here, so I can show it here. The rate of increase or decrease in revenue. So because it's a negative, the revenue is decreasing, because it's negative, is $5,000. There's the revenue per week, because we're doing it with respect to time,